Hello friends, welcome to my lecture on variational problem with moving boundaries. Here we shall discuss one-sided variations. Now first we will begin with the problem where the functional depends on two functions by and z of x of the independent variable x, and one arbitrary point x1 by 1 z, one boundary point x1 by 1 z1 is fixed, while the other point x2 by 2 z2 lies on the surface. So the surface here we have taken as the plane. So here the point which is fixed is given by 0 equal to 0, z0 equal to 0, that is origin. So x is 0, y is 0 and z is 0, and the point x2 y2 z2 moves over the fixed plane x equal to x2. Now again when we want to find the extremal of this functional, since the necessary equations Euler's equations are the f y minus d over dx f y dash equal to 0 and f z minus d over dx f z dash equal to 0. So here we are given f x by z, x by dash z dash equal to y dash square plus z dash square plus 2 y z. From the equation from f x by z, y dash z dash we get from this equation we get f y, because f is dependent on y, so f y is equal to 2z, f y dash equal to 2 y dash, f z equal to 2 y and f z dash equal to 2 z dash. So the Euler's equations f y minus d over dx of f y dash equal to 0, this gives you 2z minus d over dx of f y dash, that is 2 y dash equal to 0, or I can say 2z minus 2 y double dash equal to 0. So this gives you y double dash equal to z, and the other Euler's equation f z minus d over dx of f z dash equal to 0 gives us f z is 2y minus d over dx of 2z dash equal to 0. So we get 2y minus 2z double dash equal to 0, or z double dash equal to y. Now from the two equations y double dash equal to z and z double dash equal to y, what we obtain? The fourth order derivative of y is equal to second order derivative of z, which is equal to y. So we get d4 minus 1y equal to 0, and where d denotes d over dx. Now so our auxiliary equation here is m4 minus 1 equal to 0. We can write the roots of this equation, m plus minus 1 plus minus I. So y is equal to c1 e to the power x plus c2 e to the power minus x plus c3 cos x plus c4 sin x. Now since e to the power x, we know e to the power x is cos hyperbolic x plus sin hyperbolic x, e to the power minus x is cos hyperbolic x minus sin hyperbolic x. So this equation can also be written in terms of the hyperbolic functions. So we can write it as or y equal to c1 cos hyperbolic x plus sin hyperbolic x plus c2 times cos hyperbolic x minus sin hyperbolic x plus c3 cos x plus c4 sin x. C4 sin x, and then collecting the coefficients of cos hyperbolic x and sin hyperbolic x, one can write it as by equal to C1 plus C2 cos hyperbolic x plus C1 minus C2 sin hyperbolic x plus C3 cos x plus C4 sin x. Now C1 plus C2 and C1 minus C2 can be replaced by new arbitrary constants, and then we have, so using new arbitrary constants we can write y equal to C5 cos hyperbolic x plus C6 sin hyperbolic x plus C3 cos x plus C4 sin x. Now what I want to demonstrate is that the roots of the auxiliary equation are plus minus 1 plus minus I. So in this case the solution of the fourth order linear differential equation with constant coefficients d4 minus 1 by equal to 0 can also be expressed in this form. So I have written it in the form of cos hyperbolic and sin hyperbolic and trigonometric function sin x cos x. So by I have written as C1 cos hyperbolic x plus C2 sin hyperbolic x plus C3 cos x plus C4 sin x, and then z is by double dash is equal to z. So we can differentiate this by twice. When you differentiate by with respect to x, we get derivative of cos hyperbolic x. Derivative of cos hyperbolic x is sin hyperbolic x, and derivative of sin hyperbolic x is cos hyperbolic x. This we can see easily here. Sin hyperbolic x is e to the power x minus e to the power minus x by 2, and cos hyperbolic x is e to the power x plus e to the power minus x by 2. So d over dx of sin hyperbolic x is cos hyperbolic x, and d over dx of cos hyperbolic x is sin hyperbolic x. So we can differentiate by twice, and then we will get z. Y double dash is equal to z. So z will be C1 cos hyperbolic x plus C2 sin hyperbolic x minus C3 cos x plus C4 sin x. Now we are given that y 0 and is equal to 0, z 0 equal to 0. So putting y 0 equal to 0 here, what we get? Cos hyperbolic 0 is 1, so we get C1 sin hyperbolic 0 is 0, and then cos hyperbolic 0, cos 0 is 1, so we get C1 plus C3, this term is 0. So C1 plus C3 is 0, and z 0 equal to 0 gives C1, then we get minus C3. So C1 minus C3 equal to 0. So C1 plus C3 equal to 0 and C1 minus C3 equal to 0 imply C1 equal to 0, C3 equal to 0. Now at the moving boundary point x2, y2, z2, since the boundary point x2, y2, z2 lies on the surface, we have the other conditions. F y dash at x equal to x2 is 0, f z dash at x equal to x2 is 0. So f y dash here, if we find f y dash is 2 y dash and f z dash is 2 z dash. So f y dash at x equal to x2 is 0 means y dash at x equal to x2 is 0, and f z dash at x equal to x2 is equal to 0 implies z dash at x equal to x2 is 0. Hence what we get is we have the following equation: C1 equal to C3 equal to 0 gives you y dash from this equation, y equal to C1 cos hyperbolic x. We have found C1 equal to 0, C3 equal to 0. So this reduces to C2 sin hyperbolic x and C4 sin x. This is y, and z has become C1, C3, 0. So C2 sin hyperbolic x plus C4 sin x. Now y dash is at x equal to x2 is 0. So y dash is equal to C2 cos hyperbolic x plus C4 cos x. Y dash at x equal to x2 is equal to 0 gives you C2 cos hyperbolic x2 plus C4 cos x2 is equal to 0, and z dash z dash is equal to c2 cos hyperbolic x plus c4 cos x. So z dash at x equal to x2 is equal to 0 gives you c2 cos hyperbolic x2. Okay, so by 4 minus y equal to 0 gives you d4 minus 1 by equal to 0, where d is d over dx. Now the auxiliary equation is m4 minus 1 equal to 0, so m is equal to plus minus 1 plus minus I, and so we can write by equal to c1 e to the power x plus c2 e to the power minus x plus c3 cos x plus c4 sin x. By double dash minus z equal to 0 and z double dash minus by equal to 0 together give us the fourth derivative of by minus by equal to 0, because fourth derivative of by here is equal to second derivative of z, and second derivative of z is equal to by. So by fourth derivative of by, fourth order derivative of by minus by is equal to 0, and this can be written as d4 minus 1 by equal to 0. Now the auxiliary equation is therefore m4 minus 1 equal to 0, so which gives the roots plus minus 1 plus minus I, and thus y is equal to c1 e to the power x plus c2 e to the power minus x plus c3 cos x plus c4 sin x. Now since e to the power x is equal to cos hyperbolic x plus sin hyperbolic x, and e to the power minus x is cos hyperbolic x minus sin hyperbolic x, this solution of the equation d4 minus 1 by equal to 0 can be also written as by equal to c1 cos hyperbolic x plus c2 sin hyperbolic x plus c3 cos x plus c4 sin x, and that is in terms of the hyperbolic functions and the trigonometric functions. So we have written the solution of this equation in terms of the hyperbolic and cosine sine functions. So by equal to c1 cos hyperbolic x plus c2 sin hyperbolic x and c3 cos x plus c4 sin x, and by double dash is equal to z. So when we differentiate this by twice, we can see that derivative of cos hyperbolic x from here is e to the power x plus e to the power minus x by 2, and sin hyperbolic x is e to the power x minus e to the power minus x by 2. So this gives you give you d over dx. Cos hyperbolic x is sin hyperbolic x, and d over dx of sin hyperbolic x equal to cos hyperbolic x. So by taking the derivative of y with respect to x twice, we get the expression for z, c1 cos hyperbolic x plus c2 sin hyperbolic x. This is minus c3 cos x. This gives us the c4 sin x gives, after twice differentiating, we give minus c4 sin x. So now let us apply the conditions by 0 equal to 0 and z 0 equal to 0. When you put by at x equal to 0 as 0, what we get is c1 plus c3 equal to 0, and z 0 equal to 0 gives us c1 minus c3 equal to 0. So the two equations c1 plus c3 equal to 0 and c1 minus c3 equal to 0 imply that c1 equal to c3 equal to 0, and so then the expressions of y and z reduce to, thus y becomes c2 sin hyperbolic x plus c4 sin x, and z is equal to c1 and c3 are 0. So c2 sin hyperbolic x minus c4 sin x. Now let us apply the condition f by dash at x equal to x2 is equal to 0, which is which are the conditions which we get by the moving boundary point x2 by 2 z2 which lies on the surface of the plane. So, f by dash x equal to x2 gives by dash at x equal to x2 equal to 0, because f x by dash f x y z y dash z dash is this by dash square plus z dash square plus 2 y z. So, f y dash gives 2 y dash, f z dash gives 2 z dash. So, we will get here 2 y dash at x equal to x2 0 or by dash at x equal to x2 0, and 2 z dash at x equal to x2 equal to 0 gives z dash at x equal to x2 0, and so here y dash will be 0 at x equal to x2, and therefore we differentiate this equation with respect to x and put x equal to x2 equal to 0. So, we get by dash is equal to C2 cos hyperbolic x plus C4 cos x, and z dash is equal to C2 cos hyperbolic x minus C4 cos x. So, by dash at x equal to x2 equal to 0 implies C2 cos hyperbolic x2 plus C4 cos x2 equal to 0, z dash at x equal to x2 equal to 0 gives us C2 cos hyperbolic x2 minus C4 cos x2 equal to 0. So, we get this equation and this equation. Now, these equations we get. So, here if cos x2 is not equal to 0, if cos x2 is not equal to 0, then what we will get is, let us subtract this equation from this equation. So, what do we get? 2c4 cos x2 is equal to 0. So, if cos x2 is not equal to 0, then C4 is equal to 0, and C4 is equal to 0 implies C2 cos hyperbolic x2 equal to 0. Now, cos hyperbolic x2 is equal to e to the power x plus e to the power minus x by 2. So, it is always greater than or equal to 1, and therefore, this is never 0. So, this implies C2 is equal to 0. Now, C2 and C4 is equal to 0. So, therefore, extremum is attained on y equal to 0, z equal to 0. Now, because y is equal to C1 cos hyperbolic x, C2 sin hyperbolic x plus C3 cos x plus C4 sin x, C1 C3 are 0 already, and we now get C2 C4 are zeros. So, y is equal to 0, similarly z equal to 0. So, the extremal is attained at y equal to 0, z equal to 0, but if cos x2 is equal to 0, if cos x2 is equal to 0, then what we will get? If cos x2 is equal to 0, then C2 cos hyperbolic x2 is equal to 0. Then C2 cos hyperbolic x2 equal to 0 implies C2 equal to 0, and C2 equal to 0 implies C4 cos x2. So, C4 cos x2 equal to 0 and is true for arbitrary C4. Okay. So, C2 equal to 0 and C4 is arbitrary. So, in this case y will be equal to, we have C1 C3 equal to 0, C2 is equal to 0. So, y equal to C4 sin x and z is equal to minus C4 sin x. So, the extremal will occur here, y equal to C4 sin x, z is equal to minus C4. So, this is the solution of this problem, where we have taken one point fixed and the other point varies on the plane. Now, let us take the case of one sided variation. So, here what we will happen is that we are given a functional I y x equal to integral x1 to x2 f x by y dash dx. Let us suppose that there is a restriction which is imposed on the class of permissible curves in such a way that the curve can pass through points of a certain region R bounded by the curve psi x y equal to 0. So, we have a certain region R which is bounded by the curve psi x y equal to 0. The restriction is imposed on the class of permissible curves that those curves can pass only through this region, and in such a problem the extremizing curve C either passes through a region which is completely outside R, or C consists of arcs lying outside R and also consists of parts of the boundary of the region R. Now, so here we assume that the derivative of f with respect to y dash twice is not equal to 0. This assumption is a valid assumption in many variational problems. This means that the arcs of the extremizing curve C lying outside the region R meet the curve the boundary curve of R tangentially. Let us study a problem on this article. Let us consider this problem. Find the shortest distance, shortest path A minus 2 3 to the point 2 B 2 3 located in the region by less than or equal to x square. Let us see the curve, the boundary curve of the region by less than or equal to x is given by equal to x square. So, this is the curve by equal to x square. Now, we are given that by is less than or equal to x square. So, this region is by less than or equal to x square. Now, we have to find that path which is the shortest from the point minus 2 3 to the point 2 3. So, the point is here, let us say minus 2 3, and there is a point here 2 3. The 2 points are symmetric with respect to the y-axis, and so we have to find the shortest path from the point minus 2 3 to the point 2 3, which is located in the region by less than or equal to x square. So, we have to find the path which is shortest from the point minus 2 3 to 2 3 and does not cross this curve y is equal to x square. It lies the path must lie in the region by less than or equal to x square. So, we have to extremize here I y x equal to integral over minus 2 to 2, x varies from minus 2 to 2 under root 1 plus y dash square dx. Now, subject to the conditions that y is less than or equal to x square and y minus 2 is equal to 3, y 2 is equal to 3. By Euler's theorem, we know that the extremals of this functional, okay, under root 1 plus y dash square dx, the extremals are straight lines. This we have seen earlier in a lecture, that y is equal to c1 x plus c2. Now, if f x by y dash is under root 1 plus y dash square, then we can see that here f x by y dash is equal to under root 1 plus y dash square. So, when we differentiate it partially with respect to y dash, we get y dash divided by under root 1 plus y dash square. Let us differentiate it again. So, what we get, derivative of this with respect to y dash is 1, then under root 1 plus y dash square minus 1 by 2 under root 1 plus y dash square into 2y dash divided by 1 plus by dash square. So this gives you 1 plus by dash square minus by dash square. So 1 upon 1 plus by dash square to the power 3 by 2. So and this is clearly not 0. Hence the desired extremal will consist of portions of the straight line AP and QB both tangent to the parabola. So what we will happen is this will touch, this is let us say A, this is B, this is AP, this is BQ. So the extremal will consist of the portions of the straight line AP, QB and both tangent to the parabola y equal to x square and of the portion POQ. POQ. So AP and QB will be tangent to the parabola, and so this is the extremal minus 2 3 2 P, that is the straight line AP which is tangent to the curve y equal to x square, then the arc of the curve POQ, and then the straight line QB which is tangent to the parabola at the point Q. So let us see that let us say that the abscissa of P and QB minus x bar and x bar respectively. So let abscissa of P be minus x bar because they are symmetric. So and abscissa of Q be x bar. Then the condition of tangency of AP and BQ at P and Q gives, now dy by dx y is equal to C1x plus C2. So dy by dx is equal to C1, okay. At the point y is equal to x square. So at the point of contact the slopes must be same. So dy by dx will be equal to 2x, and therefore at the point of contact x bar at Q, we will have 2x bar is equal to C1. Uh, 2x bar equal to I have taken here C1 plus C2x, C1 plus C2x. So I will get here C2, and therefore this will be 2x bar is equal to C2. Furthermore, x bar y bar lies on the parabola. So then let us say this is x bar y bar, and this is minus x bar y bar, the point P. So x bar y bar lies on the parabola as well as on the line y equal to C1x plus C2x. So y bar is equal to C1 plus C2x bar, and y bar is also equal to x bar square. So we can say that C1 plus C2 x bar is equal to x bar square, and we have C2 equal to 2x bar from the condition of tangency. So C2 is equal to 2x, x bar is equal to C2 by 2. What we get is C2 equal to 2x bar. So QB passes through. Now moreover, this line QB passes through 2 3. So what we get, y equal to C1 plus C2x gives you 3 equal to C1 plus 2C2. Since QB passes through this 2 3 point. So we get 3 equal to C1 plus 2C2. Now from these equations, this equation and this equation C1 plus 2 C2 equal to 3. We can put here x bar equal to C2 by 2, or we can say, and then simplify. Okay, we will get x1 bar, we get two values, x1 bar is equal to 1 and x1 bar, x2 bar is equal to 3. We get two values of x bar. One value is we have taken as x1 bar, x1 bar is 1 or x2 bar is 3. So, there are two values of x bar, one is x1 bar which is 1, and another value of x bar we have taken as x2 bar is 3. Now, what happens is x bar, x1 bar is equal to 1 and x2 bar is equal to 3. These are two values of x bar. So, x2 bar equal to 3 is not possible because x2 bar because x bar lies between 0 and 2, since 0 is less than x bar less than 2. So, x2 bar is equal to 3 is not possible. So therefore, we take x1 bar equal to 1 and x1 bar equal to 1. So, we will get the following extremal. We had C2 equal to 2x bar. So, since x1 bar is equal to 1, we have C2 equal to 2, x bar is equal to 1 is admissible. So, we get C2 equal to 2 and we have C2 equal to 2. So, we get C1 equal to C1 plus C2 equal to C1 plus 2 C2 equal to 3 gives us C1 equal to minus 1. Now, what happens? So, bi is equal to C1 plus C2x. So, bi is equal to minus 1 plus 2x. Okay, so bi equal to 2x minus 1 is the equation of the line QB, and for the line AP we shall have minus x bar by bar are the coordinates of this bi equal to C1x plus C2x. So, the slope of this line is dy over dx is equal to what we have, dy over dx equal to 2x, and so 2x means x1 bar is equal to 1. So, minus x bar minus x1 bar. So, dy by dx will be minus 2 at this point, dy by dx will be minus 2. Okay. So, bi will be equal to minus 2x minus 1. When we take x is equal to minus 1, it will be 2 minus 1. C1 will be equal to C1 is equal to minus 1. So, we get x1, it passes through minus x bar by bar. So, minus x bar means minus 1, and by bar is equal to when we take bi is equal to C1x plus C2, in this case bi comes out to be 1. So, this will be x is equal to 1. So, bi is equal to 1. So, this is 1 point. So, this is minus 1 point. So, here so the equation will be minus 2x minus 1, that this is the equation of PA. Equation of PA will be bi equal to minus 2x minus 1. Equation of QB will be bi equal to 2x minus 1. So, the extremal will have the equations y equal to minus 2x minus 1 from minus 2 to minus 1. The extremal will coincide with the tangent with the line straight line AP, which is tangent to the parabola at the point P. The equation of AP is y equal to minus 2x minus 1. So, y equal to minus 2x minus 1 when x lies from minus 2 to minus 1, and then the arc of the parabola POQ. So, from minus 1 to 1 y is equal to x square, and then from the point 1 1 to the point to the point 2 3, that is 1 is less than or equal to x less than or equal to 2, we have y is equal to 2x minus 1. So, this is the extremal. Extremal consists of the straight lines AP, arc POQ and the straight line segment QB, and their equations are given by this. Now, let us take another problem. Here we have to extremize the functional I equal to integral over minus 3 to 3 y dash square dx, where y assumes value 1 at x equal to minus 3 and it assumes value 3 when x is equal to it assumes the value 1 when x is equal to 3, and it is subject to the condition that the admissible curve cannot pass inside the area bounded by the circle x square plus y square equal to 5. Now, here we have the circle x square plus y square is equal to 5. At minus x equal to minus 3, y is equal to 1. So, this is let us say the point minus 3 1, and this is the point 3 1. The condition is given that the admissible curve cannot pass inside the area bounded by the circle x square plus y square equal to 5, and the circle is this. Now, the curve, okay, these straight line segments, straight lines will be tangent to the curve, like this. So, we have the circle x square plus y square equal to 5, it is denoted by the curve ACB, ACB. ACB, and let us say this is P and Q. You can see that the curve does not pass through the area, this one. Now, R, let us say R be the region interior to the circle, R be the region interior to the circle. So, we are to determine the extremal of this function, that is we have to find the path between the points minus 3 1 and 3 1 in such a way that the curve cannot pass inside the region R, and this is to be extremized. Now, fx by y dash is equal to y dash square here. So, from the Euler's theorem, fy minus d over dx fy dash is equal to 0, and this gives you d over dx of 2y dash equal to 0, because f is independent of y. So, delta f by delta y is equal to 0, delta f by delta y dash is 2y dash. So, this gives us 2y double dash is equal to 0, and 2y double dash is equal to 0 gives y equal to c1 x plus c2, where c1 and c2 are arbitrary constants. So, extremal of the functional 2, extremal of this functional are straight lines. Now, since f by y dash f by y dash f by dash by dash, here you can see f by dash is 2y dash and f by dash will be 2. So, f by dash is not equal to 0, and therefore, the required extremal will consist of portion of the straight lines P1A let me call it as P1A and this as P2B. So, P1A, P2B which are tangents to the circle one end of the portion ACB of the circle as shown here, ACB of the circle as shown here. Let the coordinates of A and B be minus x1 by 1 and x1 by 1 respectively. So, this is minus x1 by 1 and the coordinates of this are x1 by 1. Since A and B lie on the curve x square plus y square equal to 5, the parabola, the circle. So, x1 square plus y1 square is equal to 5. Now, from the coordinate geometry we know that if we draw a tangent to the curve x square plus y square equal to a square at the point x1 by 1, the equation of tangent to the circle at the point x1 by 1 is x1 plus y1 is equal to a square. So, making use of this we have the equations of the tangent lines P1A and P2B as minus x1 plus y1 equal to 5 and x1 plus y1 equal to 5. Now, this x1 plus y1 equal to 5 also passes through the point P2 which is 3 1. So, let us put the coordinates here, x equal to 3, y equal to 1. So, we get y1 equal to 5 minus 3x1. Now, y1 equal to 5 minus 3x1 we put in this equation, x1 square plus y1 square equal to 5, and then we get the values of two values of x1. They are 2r1 and x1 is 2r1. Now, let us see x1 is equal to, and corresponding values of y1 are, and the corresponding values of y1. y1 are minus 1 and 2. Okay, so the coordinates of B will be either 2 minus 1, okay, coordinates of this point. Coordinates of B are 2 minus 1, okay, 2 minus 1 are 1 2. Now, clearly the coordinates of B cannot be 2 minus 1, okay. So, because B lies in the first quadrant, so the coordinates of B we take as 1 2 and the corresponding coordinates of A are therefore minus 1 2, okay. So, taking B as 1 2, A becomes minus 1 2. Now, putting x1 equal to 1, we have x1 equal to 1 here, y1 equal to 2 in these equations 6 and 7, we get the equation of the tangent lines P1A and P2B, and they are the equation of the tangent at A is minus x plus 2y equal to 5, and the equation of the tangent at the point B is x plus 2y equal to 5. So, the required extremal, therefore, let us see, we have equation of P1A is minus x plus 2y equal to 5, or y is equal to 1 by 2x plus 5 by 2, and equation of P2B, it is x plus 2y equal to 5, or y is equal to 1 by 2 minus y is equal to minus 1 by 2x plus 5 by 2. So, we have the required extremal as y equal to x by 2 plus 5 by 2, y equal to x by 2 plus 5 by 2, that is tangent P1A, and it is from minus 3 to 1, minus 3 to minus 1, from P1 to A is having coordinates minus 1 1, minus 1 2. So, for the tangent P1A, x varies from minus 3 to minus 1, and then the arc of the circle from A to B, that is ACB, and the equation of that is 5 minus x square square root. We are taking y to be positive because AB lies above the x axis. So, arc ACB, so from minus 1 less than or equal to x less than or equal to 1, and then the tangent P2B. Tangent P2B is y equal to minus half x plus 5 by 2 from the point x1 by 1 to the point 3 1, x1 by 1 is 1 2. So, x varies from 1 to 3. So, this is how we find the extremal for this problem. So, with this I would like to conclude my lecture. Thank you very much for your attention.